partially talked about the next mode of transfer, which was radiation, right? So you already know that in radiation, don't require any medium transfer the heat, right? Without the medium, this thermal radiation propagates. And these are the some properties of the thermal radiation, right? And yeah, so this is the wavelength of that thermal radiation. And if the temperature of any object is above 0 degree Kelvin, then it will emit thermal radiation. So that is the property of radiation, right? And then we have to firstly talk about some terminologies associated with this thermal radiation, right? So first terminology would be, let's say that so the first terminology would be that, let's say if this is some material and some thermal radiation is falling on this material. So this is one, this would be one, that the thermal radiation is falling on. And the second would be that we'll talk about some radiation in which it is emitting. So right. So in first case, we'll talk about all the terms in which this is thermal radiation is falling, right? And then we'll talk about thermal radiation emitting. So these things we'll talk about, right? So first, let us talk about that the thermal radiation is falling on this material, right? Then what will happen? So this tells us about the reflectance, reflectance, transmittance, and absorbance. Right, so these are the peculiar three properties associated with the thermal radiation falling on the object, right, on a material. So let's say that this is some material, right, and the thermal radiation is falling on, right. So one case would be that this is getting reflected. So that would be, let's say, write it as QR. Some would be absorbed, right. So let's say that is QA, and some would be transmitted. So that would be QT. So these three scenario can happen, right? So first, let us define what is reflectance, right? So what is reflectance? So it is the ratio of total, right? So it is the ratio of the energy or whatever the radiation reflected over the total thermal radiation falling on the material. Right, so how do we represent that? So this is represented by R, and this would be how much? This would be QR divided by Q. This would be called reflectance. Similarly, we will have transmittance. And what would be transmittance? Again, it is the ratio of energy transmitted over the total energy falling on the material. Right. So again, this is denoted by T, and this would be how much? That would be Q divided by total. Similarly, we will have transmittance, and then we have absorbance. So the ratio of energy absorbed over the total radiation energy falling on the material. Right. So this would be A, and this would be QA divided by Q. Right. And we know that this was the total Q, right, which was falling on this surface. So this part, some of the part is getting reflected, some of the part is getting absorbed, some of the part is getting transmitted. So if we combine all these three, so that would amount us to be Q, right? So if we calculate sum of reflectance, sum of transmittance, sum of absorbance, so that would be how much? That would be QR by Q plus QT by Q plus QA by Q. So that would be QR plus QT plus QA by Q, and this is Q by Q, so that would be 1. So sum of reflectance, transmittance, and absorbance would give you 1. This is very important condition. And let's say if you have a perfect reflector, right? If you have a perfect reflector, so then all the energy, whatever energy is falling on that material, if this material is perfect reflector, then what will happen, guys? What will happen? Whatever amount is falling, yes, yes, what are you saying? If we have a perfect reflector, then it will, whatever amount of radiation is falling, total amount would be reflected back. No absorption, no transmission will take place, right? So which means that absorbance would be zero, transmittance would be zero, right? Which means that R would be 1, and if R is 1, then T and A would be. Similarly, if we have a perfect transmittance or transmitter, then T would be 1, and R and A would be 0. And if we have a perfect black body, right, for absorption, we say that a black body. So if we have a perfect black body, then A would be 1, and T would be 0, R would be 0, right? And similarly, if transmission is 0, yeah, so can be different scenarios as well, right? So let's say that R plus T plus A is 1. So if your T is 0, right, then it means that R plus A would be 1. So if the material is a good absorber, if the material is good absorber, then this would be higher and this would be less, right? So these are the different conditions that we have for different kinds of material. And these cases arise when the heat is falling, right? When the thermal radiation is falling on some materials. Please note down these terminologies. These are very important and we'll use them in yeah, upcoming topics. We'll use them. So please note down these things. If you guys have any question, please tell me. 1 minute, guys. Yeah. So whenever you guys want me to scroll down, please tell. Yeah, whenever you guys have noted it down, tell me. You have to hurry because we have covered three main topics, which is Stephen's law, then we have Newton's law of cooling, and then we have this black body effect. So these three topics I want to cover. Please note it down.
Done, sir.
Then, so then please, whenever you guys have completed this step. And can you guys tell me what would be the units of these reflectance, transmittance, absorptance? What would be the units? Yes, what would be the units? Can you guys tell?
So I
Yeah.
I didn't understand that.
Oh, you didn't understand which part? Yes,
Uh, the absorbed thing.
absorptance. You didn't understand this part.
Yes, sir.
Yeah. So let's say that on some material, right? Let's say on some material, 50 joule is radiation heat is falling on, right? And let's say this material absorbs some heat, right? This material absorbs some, let's say 20 joule is absorbed by that material. Then the absorbance of that material would be how much? That would be 20 divided by 50. So that is called the absorbance, right? Whatever amount of heat, thermal radiation energy that is falling on that material, right? So let's say the sun, the radiation coming from the sun, that is falling on some material, right? Some material is getting heated due to the absorptance of that thing, right? So that is called the absorptance. Did you understand that part?
Yes, sir.
Yeah. So the heat absorbed, right? Heat absorbed divided by the heat or the energy, thermal radiation falling on that material. So that is called the absorptance, right? Yeah, and all these three quantities would be unitless, right? Because in the numerator, if you have energy, in the denominator, you have energy. So energy by energy. Then this is a ratio, then that would be unitless, right? So,
Yes, sir.
yeah, whenever you guys have completed, please tell me. Yes, whenever you guys have completed, please tell me. Yeah, noted everyone.
Yes, sir.
Okay, so then, so now we were talking about the terminologies associated when the thermal radiation was falling on the material. But we know that every material, right, every material above the 0 degree Kelvin temperature will also emit radiation, right? Then what are the terminologies associated with the emission of the radiation, right? So let us talk about that. So in this part, we will talk about emissive power, and then we will talk about absorptive power, and this is very crucial, emissivity, right? So this is very crucial that. So we have to understand these things very carefully, right? So what is emissive power, right? So there are two kinds of emissive power, right? One is called monochromatic radiation or monochromatic emission. Or this is also called spectral emissive power, and the other one is total emissive power. Right. So these two things we will understand. So what do you understand by monochromatic? Have you guys heard about this monochromatic? Yeah. Have you guys heard about this monochromatic thing?
No, sir.
Okay. So monochromatic is made up of, as we can see, two words, mono and chrome. Right. Mono means single, chrome means wavelength. So if we have some radiation which have only one wavelength, so that kind of emission would be called monochromatic emission. So monochromatic emission would be related with the wavelength. Okay, so let us define this monochromatic emission. So it is defined as the energy emitted. So now you see that this is emitted, right? Energy emitted per unit time and per unit area and per unit wavelength, right? So this would be called the monochromatic emissions. Monochromatic emission is defined as energy per unit time and area and the wavelength. So this would be called monochromatic emission. So some material is emitting some energy, right? Thermal radiation, and if we calculate this energy per unit surface area, right? From this area, how much energy is getting emitted, and then we divide it by time, then we divide it by area, and then we find out for different colors, right? So let's say if we find out for red color light, if we find out for yellow color light, and if we find out for, let's say, blue color light. So for all these different color of light, this is dependent upon wavelength, right? So in your 10th standard, you guys have understood that all these different colors have different wavelength. So red one has the biggest wavelength, and this blue one has the VGO. So this one has a lower wavelength as compared to this red. So when we filter these things, right? If we make a red filter, yellow filter, blue filter, then that energy emission would be dependent upon the wavelength, right? So that is called the monochromatic emission. And you guys can see that the unit would be how much? So unit would be joules per second, and this is area and this is wavelength. So that would be meter per right. So that would be the unit of this monochromatic emission. Now, if we calculate the total emissive power, right? Total emissive power. So that would be how much? So that would be when we integrate monochromatic emission, or simply if I write it down. So this is total energy emitted per unit time and area. So that would be total emissive power. And how do we represent that? So this would be E. And this is related with 0 to infinity E lambda and T lambda, right? So if we integrate over all the wavelengths from 0 to infinity, if we integrate over all the wavelength, so that would be total emissive power. Is this clear, guys? Is this
Yes, sir.
and what would be the unit of this thing? So unit would be joules per second per meter square. So that would be the unit. Or we can also write this as watt per meter square. So we can write it also. So this is emissive power, and then we have absorptive power, right? Absorptive power. Again, this is of two types. One is monochromatic absorption, and the other one is total absorption, absorptive power, right? So again, how is this monochromatic? Now, absorption would be related with the heat coming at the thermal heat falling on that material, right? So that would be absorption. So this absorptive power, it is defined as this monochromatic. So monochromatic absorptive power. This is defined as, so it is the ratio of energy absorbed at a particular particular time over the total energy falling on the material, right? Over a particular wavelength. So this is defined by what? A lambda, right? This is E at energy absorbed at particular time, right? So let us write this as simply as A lambda. This is A lambda. And this is unitless, right? Why this is unitless? Because you see that this is energy divided by energy. So if it is energy by energy, then this would be unitless, right? And then if we calculate the total absorptive power, so that would be what? That would be simply the whole integration. A lambda 0 to infinity and T lambda. So this is what we call the total absorptive power. And then lastly, And then lastly, we define this emissivity. Right? These are very crucial. These are very crucial terminologies, and we have to remember them. So emissivity is the total emissive power over it is again. So it is the ratio of total emissive power of a body over the emissive power of a black body at a particular temperature. Right, so this would be how much? So emissive power of total emissive power of a body is E. Total emissive power of a black body is E, and that would be called emissivity. Right, so emissivity is this is the emissivity, and this is very important in understanding the Stephen's law. Right, so this part will come in the Stephen's law. Right, so let's say if you know the emissive power of a black body, right? Let's say if you know the emissive power of a black body, power of black body, and then you want to calculate the emissive power of a body, then how can you calculate? You will multiply the emissivity with the total emissive power of the black body, right? Is this thing clear, guys?
Yes, sir.
Yeah, and then yeah, so let me again do this last part, and then yeah, I will give you guys to some time to note it down, right? Okay, so, yeah. Then last we have to understand this Kirchhoff law. And what does it say? It says that the ratio of monochromatic monochromatic emission emission and absorptance is a constant, which is equal to the emissive power of a black body at that particular wavelength. Right, so E lambda divided by A lambda, that is a constant, and that is given by this E lambda. Right. So this is what this emissive power of this black body is. Right. So you guys please note it down, and you guys can see that if you have a good emitter, so that would be a good absorber also, right? Because this thing is a constant. So if you have a good absorber, so then that would be a good emitter also. So that is why black body is a good absorber as well as a good emitter. So that is why this black body is very special. You guys please note down all these things, And then we'll talk about this Stephen's law and all the other things. Quickly note it down, please. So remember that this part we did for the emission, right?
Done, sir.
Done. Okay, then please.
Done, sir.
Yeah, whenever you guys Done. Okay, so yeah, this one is very crucial to the this is very crucial. So this emissivity relates the total emissive power of a body, the total emissive power of the black body. This is why this is very important. Whenever you guys have completed these, done everyone. Everyone are noted.
Yes, sir.
Yes, sir.
Okay, so then now we can. So now these were the terminologies that we have to remember. And remembering these things, then we can understand about the next set of properties. Right. So first one is the Stephen Boltzmann law. Right. This is Stephen Boltzmann law, and it says that the total emissive power, which is what? Which is the energy per unit time per unit area. The total emissive power of a black body varies with the absolute temperature to the power 4. Right. So to the fourth power of the temperature. So varies with the absolute temperature to the power or to the fourth power. Right. So this emissive power. Remember, this is emissive power. This is totally different from energy. This is not energy, right? Energy in this chapter we are denoting by Q, right? So this emissive power that is directly proportional to T to the power 4. And if we remove this proportionality, so then we'll get the sigma, which is sigma to T to the power 4. This is very important relation, right? So this sigma is called the Boltzmann constant or Stephen's constant, right? This is the Stephen Boltzmann constant. And how much is this value? So this is, I guess, here let me check that. So this value is 10 to the power minus 8, 5 into 10 to the power minus 8. Check that. 5.67 and 10 to the power minus 8. And unit you guys can see, so that would be watt and meter square and Kelvin minus. So that is the this is uh, this is the Stephen Boltzmann constant. And if we write the energy, right? So E we know that this is how much? E is Q by area and by time, right? And this is equal to sigma T4. So if we calculate this Q, so this would be how much? That would be, this is time, right? So this would be sigma A T and T to the power 4. So this would be radiant energy, right? Energy emitted. So radiant energy. And we can also calculate the power, right? So if we look at this equation, because E is Q by A. So if we look at this equation, right? Q by T is what? Q by T is what, guys? Energy by time. Energy by time is energy by time is power. So that would be power by A and sigma T. So we can also calculate power as this is radiative power, right? And all of these things we were calculating for what? We were calculating it for black body, right? Now this emissivity will come in handy. So this thing we will calculate, we were calculating for the black body, right? So if this is not a black body, for general body, right? We know that for black body, P is sigma T to the power 4. So for general body, what would be emissive power? We know that emissive power is emissivity into E. So that would be emissivity sigma T to the power, right? But when Stephen gave this law, right? But when Stephen gave this law, he didn't consider the temperature of the surrounding, right? So then if we consider the temperature of the surrounding, So when considering the temperature of surrounding, then there would be a correction. And what is the correction? So correction is that the emissive power of black body, that would be sigma T4 minus T naught. So this much amount of the emissive power would be lost due to surroundings, right? So this is what we call for the general for this correction, for the surrounding correction. So you guys please note it down. And for the general body, this would be emissivity multiplied by this, right? Where T naught is temperature of surrounding. Right? So please note down these things, and then we will talk about these things you have already noted. So please note down this. And then we will talk about uh, Newton's law of, yeah, and some questions they are there. So that question later, but Newton's law of cooling and this black body spectrum, those are important. That one. Yeah, whenever you guys want, you just scroll down. Remember this, whenever I am writing this T, so that is time. Whenever I am writing this T, so that is temperature. Don't get confused with these things. Yeah, whenever you guys have noted it down, that
Done, sir.
Yeah. Okay. So then, in the next class, I will start because this thermodynamics part that is short. So I will start oscillation and waves. Right. That is a big one. Start with that. Yeah. Whenever you guys have noted, please tell.
Done, sir.
Done. Okay. So then, yeah. Then let us start the next topic, which is Newton's law of right. So let's say you have some material, right? And its temperature is, let's say, it has some temperature, right? Now, what is happening is that the temperature of surrounding is T naught. So the temperature and this T naught is lower one, and this T is higher one, right? So then the temperature of this thing will be decreased, right? So it will cool down, and it will cool down at a certain rate, right? So the cooling down of this thing, that is given by this Newton's law, right? And that what does it say? So it says that the rate of change of rate of change of heat or radiant energy, radiant energy would be directly proportional to the temperature difference of the body and the surrounding. Right. So it says that dq by dt, that would be directly proportional to t minus t naught, right? Where where T is temperature of the body, temperature of the body, right? And then there's, let's say, T naught is temperature of environment, right? And this delta Q is the radiant heat energy. So there would be a minus sign because the energy is decreasing. So if we remove this proportionality, right, if we remove this proportionality, so that would be a K constant and T minus T naught. And if we take this thing in the right hand side, take this minus, so that would be minus K T minus T. So that is what we call Newton's law of, and we know that you guys know that how the temperature of something changes, right? That you guys already know. So how the temperature of the liquid change, you guys remember. If I want to change the temperature of some fluid from some temperature to other temperature, how the temperature changes? Yeah, you guys remember that? So let's say if I have a material and I want to change its temperature from something to something.
Latent heat.
So the state is not changing. The state is not changing.
Oh my god, a specific heat.
So specific heat, right? So we know that what is specific heat? So specific heat is MC and dt, right? Because we are writing in delta, so we can write it as MC delta T. So this we are writing as T, and this is right. So this is delta temperature T, right? So if we write this thing, so then what would be here, right? This is delta T temperature change, right? So if we write this thing in here, where this C is specific heat capacity, right? This is specific heat capacity. In NCRT, they have represented this by S, but yeah, so this means specific heat capacity, right? And we can write the value of dq from here, so that would be mc and dt, right, divided by dt, and this is minus k t minus t naught. And if we take this thing in the other side, so this would be minus k by mc and t minus t. So this k is a constant, m and c they are constant. So I can write them as capital T. Right. So let's write them as capital. These ones were small ones. So this is capital T minus T. This is another relation, right? So this will tell us the temperature change, the rate of temperature change over time. This is also Newton's law of cooling, right? In terms of the temperature change. So let's say if I take this thing, right, I want to solve this thing. So dt, and this is t minus t naught. I take this thing in here and I take this thing in the right hand side, right? So can you guys tell me, if I integrate this thing on both this side, so what I will get from here? Do you guys remember that what is integral of 1 by x? What is the integral? Yes, do you guys remember that? What is the integral of 1 by x? Hmm.
X raised to minus 2?
No, no, no. So this is what? This is x to the power minus 1 dx integral.
Log EX.
Yeah, so now you are correct. So that is, yes, that is
The
log.
other one was differentiation, right, sir?
Yeah, so what you told me earlier, what was differentiation of d by d. So this would be, yes, this would be minus 1 by x square or x to the power minus 2. Yeah. The answer that you told me was different. Integration would be log x, right? So similarly, what do we have in here? The function variable is temperature and this is the variable. So this would be ln t minus t naught and minus k, they are constant. So if I integrate this thing, what would be this thing? This would be what? This would be minus integration of dt. So that would be simply t, right? So this is minus kt plus so this would be the integral, right? And if I make this graph, right? If I make this graph, so then what I will get? If I make this graph, then this would be the variation. So this is ln t minus t naught, right? And the variation would be like, and this is time with which it is. Right. So this is the graph of Newton's, right? And why did I get this downward slope? Because this is minus k. That is why got this slope. So you guys have done this straight line, right? In your mathematics part, you guys have done this straight line. So this is something like y, which is minus mx plus c. That is the graph that I have. If I had y equals to mx plus c, so then it would have been something like let c is 0, so this would be some from here, right? So, but this is negative, so slope would be like that, right? So these are the things that we understand from Newton's law of cooling. You guys quickly note it down and then we'll do some questions. So you guys have to remember this, right? You guys have to remember this part. This part is crucial. This one and this. So you guys please note down from here and then we will do one question and then you guys will understand this part clearly. So please note it down. Remember, this is very important that whenever we are changing the temperature and the state is not changing, then we use specific heat. And whenever the change of state is happening, so in change of state, the temperature doesn't change, only the state changes. Then we use latent heat. Okay, whenever you guys want me to slow down,
Sir, can you scroll down?
Yeah, whenever you done. Okay, so yeah, then let us do a question which is very important, and then we black bodies. Right? All these things so we have done. So this is the power, right? And, okay, so this is right, and here they have written MS, right? But we are writing MC. Get confused with right. This is the ground. Okay, so let us do this question. So a pan filled with hot food cools from 94 degrees C to 86 degrees C in 2 minutes, right? So the relation that we have is this one, right? So this is the relation that we have. So dt by that is equal to what? Let's say k, and let us ignore that part, negative part. This is T minus T, right? This is temperature of surroundings, environment. This is the temperature. So in here, we write the average temperature. Always remember, in here we write the average temperature. And this is the temperature change. So let us do this question. A pan filled with hot food cools from 94 degrees C to 86 degrees C in 2 minutes. So what is the temperature change, guys? Temperature change is because this is negative and negative it will, so we'll write 94 minus 86, right? And this is
Yes.
how much? So this is 4 minus, this is how much? 4 minus 6, 8. So 8 degrees C divided by 2 minutes, right? This is the time change. And then we have to calculate the average temperature. So average temperature is what? Average temperature is
Uh, nine.
plus 80.
94 plus by 2.
So this is how much? 0, 80, right?
180 by 2, which is
Oh yeah, 180. 970.
so 9
90.
90.
So K 90 minus what is the temperature of the surrounding? When the room temperature. So temperature of surrounding is 20. So this is 20. Right. So then what we can calculate? Then we can calculate this K, which is 4 by 70. Right. So K we have calculated. Now, how long will it take to cool from 71 degrees C to 69 degrees C? Then what is the temperature change, guys? What is the temperature change in here? So this is first thing, right? It is, yeah, one. And then again, what is temperature change? And T minus T. So again, temperature change is how much? 71 to 69, 2 degrees C, right? Divided by time we have to calculate. So let's say time is X, right? And equals to K we have found out 4 by 70. What is the average temperature? 71 and 69, what is the average temperature? Yes, what is the average temperature?
140 by
Yeah,
2, which is 70.
70. So that would be 70 minus temperature of surrounding is 20. So this would be how much? 2 by X, 4 by 70 into this is 50. So this will cancel. This will cancel. Right. So then how much we will get? So X would be 7 divided by this 10. Right. So X would be 7 by 10 minutes, which is how much second? 7 by 10 into 60. This is 42 seconds. Right, so this would be the answer. Did you guys understand this part? Yes, this is the first part.
Yes, sir.
Please note down. This question is very important. Please note down. Right. Please note down this part and yes, I have not written it properly. Guys, okay. Okay, one topic that that will be the next class, and we will also start the next uh, quickly note it down and then see you in the next